Now we're moving on to a discussion of coastal processes and coastal landforms. But we're going to actually start out talking a little bit about the tides, which of course play a pretty big role in how wave action ultimately creates landforms. Tides are produced as a result of the moon and the sun's gravitational force on the oceans of the Earth. Every day there are two high tides and two low tides, also known as flood tides and ebb tides per day. And this is because the moon in particular pulls on the ocean, and as it pulls on the ocean, centrifugal force produces a bulge as well on the opposite side of the planet. As the Earth rotates on its axis, the Earth essentially rotates through these two bulges, producing the highs and the low tides. When the moon and the sun are aligned, the moon's gravitational force is augmented by the sun's gravitational force, and we have our highest high tides, and we also have our lowest low tides. These are known as spring tides and can be seen both in figures A and B. When the moon is either in the first quarter or the last quarter, in other words, it's perpendicular to the sun, its gravitational forces are not as strong as they are during those spring tides. This is when we have the lowest high tides and the highest low tides, or the neap tides. But it's worth noting before we go on that it's not quite that simple. Tides vary a great deal around the world. As you can see in this diagram down here, many parts of the world have true what are called semi-diurnal tides, which means that there are two highs and two lows a day. Others have what are called diurnal tides, which happen just once a day, as shown in the little yellow marks that we can see on the map. And then many places have a mix of the two. And I have three examples up here of different tidal stations taken from NOAA data. At the top, we see a fairly traditional semi-diurnal tide. This is actually located in Long Island. Down here in the Gulf, we see a diurnal tide. And finally, I believe this is San Diego, we see a mix of diurnal and semi-diurnal. This diagram here for each of the tidal areas shows the daily tidal patterns. Over here we see the monthly tidal patterns, and you can see the great amount of variation, particularly in the mixed semi-diurnal tides. In addition to this, the weather can impact the tides as well. When very strong storms are in the ocean, it can produce a storm surge, and this can make high tides higher than they should be. In addition to tides playing a role on coastal processes, waves do, of course, as well. This might be an obvious thing to say, but waves are the product of wind, and they're the product of atmospheric processes. As the wind is moving, the molecules of the atmosphere are moving and agitated, and as they come in contact with the surface of the ocean, it causes that energy to be transferred into the ocean. This causes the water molecules in the ocean to rotate and essentially stores the wind's energy as ocean swell. As that swell moves its way inland as a result of the blowing winds, but also as a result of tidal processes, eventually the energy in the swell gets translated into a breaking wave. And that breaking wave causes erosion in coastal areas. And then as a wave breaks, it also picks up material, carries that material, and it causes that material to be deposited. So waves are both erosional and depositional, very much like streams. As waves come in contact with various topographies within the ocean, it often produces some pretty profound impacts on the way that waves break. When waves are coming into a part of the land that sticks out into the ocean, it causes those waves to refract. And then when waves come on a regular basis at an angle in towards the shore, The waves coming in and going out produce currents called longshore currents. So refraction of waves and longshore current or drift are both very important processes that lead to coastal erosion in the formation of headland areas and embayed areas, as we can see on this diagram, but also the lateral transfer of materials along a coast. This energy of waves breaking against the coast produces various erosional features. These erosional features include cliffs that are caused by waves undercutting areas leading to mass wasting. When waves wrap around headland areas, as we saw in the diagram on the last page, it causes headlands to be eroded on both sides. That ultimately leads to the formation of arches and sea caves, and then eventually lone rocks that stick out in an area that are called sea stacks. I'm going to show you a map that shows a bunch of these things in a little bit, but it also has some of the depositional features in it, so I'm going to wait on it for a little bit. Another thing that can be produced by erosion is the creation of wave-cut platforms. If the level of the ocean changes with respect to the land, either because the ocean level is rising or because the land itself is tectonically moving upwards, you often get large flattened areas that were produced by previous erosional episodes, and that can lead to some really interesting wave-cut platforms. This is an example of a wave-cut platform in a part of Alaska called Rocky Cove, Alaska, across the inlet from the Homer area. And you can clearly see the large flattened area. Now there's a new wave-cut platform presumably being created offshore here. And as this area is tectonically lifted, we might have another wave-cut platform at some point in the future. Material that is eroded is also deposited. Some of the deposition takes place in the ocean and is essentially lost to sea level. But a lot of it is actually left behind as beaches. Beaches are nothing more or nothing less than the materials that have been broken down and physically and chemically weathered by the ocean. As longshore currents act on material that is being transported, it can create a large number of very interesting features, including barrier beaches and islands, barrier spits, baymouth bars, and lagoons. And the best way to look at these, to understand these, is to look at them on a map a little bit, but you can see them in this diagram as well. You can also see a tombolo being created. A tombolo is created when a sea stack is connected to the land by a bridge, usually because longshore currents have carried material from both ways. And I've produced a video about tombolos. Before I look at a couple of maps, because we're going to look at the Morro Bay map and the Provincetown map, let me just say that there's a real geography both to erosional coastlines and to depositional coastlines as well. And we're going to see that reflected somewhat on the next couple of maps. While the Morro Bay map is going to show erosional, some depositional features, it's largely an erosional map. And that's because it's on a west coast. And west coast in North America gets a lot more wave action than the east coast, as we'll see in Provincetown, where we have a lot more deposition taking place. So remember that the broad ocean and wind patterns that we've already talked about in this class have an impact on where we find particular features. So first, let's take a look at this Morro Bay map right here. And I'm going to actually zip down here towards the bottom of the map, where you can clearly see some headlands here. And we can also see large numbers of rocks or sea stacks in this area as waves coming in from the Pacific Ocean are refracted around headland areas. And a lot of energy is being focused on those headlands compared to the areas that are farther to the north on this map, where we have an embayed area, a more protected area, and as a result, we have more depositional material, as we see by this large baymouth bar that was started as a sand spit initially. If we look at Morro Rock right here, which is an excellent example of a very large sea stack, you can see it's connected by this causeway made mostly of sandy and pebbly material. It's a good example of a tombolo, but maybe not the best example. Now remember, this all takes place on the west coast of the United States, so there is a lot of westerly action and waves. And it's also a very young part of the world as well, with a lot of tectonic activity because of the San Andreas Fault. And as a result of that, we see a lot more erosion. Compare that to Provincetown, Massachusetts, which is built on a large sand spit. And here we can see that big sand spit all through here, and subsidiary sand spits coming off the sand spit itself that all produce this nice harbor for Provincetown. Most of Cape Cod is composed of old glacial material that has been moved by ocean currents over many tens of thousands of years, producing large numbers of spits and offshore islands. So make sure that you inspect these maps as you are inspecting the other maps as well. Just a couple last little diagrams here. This is taken from the text that shows all of the offshore islands that we see in the North Carolina area. And there are actually some really impressive features here. Not only do we have many offshore islands and bars, but there are also large numbers of spits as well. And in fact, some of what we see is estuaries that transport material into this area, and we have some interesting features that could almost be seen as delta-like features too, that's all caused in this area. And then the last thing that I just want to mention, and there is a video that talks about this as well, is the formation of coral atolls. Coral atolls are a special kind of tropical island that are formed by coral reef, and they are started when an island in a warm tropical ocean has coral reef growing around it, first as fringing reef, but because of the erosion of the mountain and changing sea levels over time, the mountain starts to go away, but the coral keeps on growing until eventually you get these very beautiful but also very low elevation ring-like islands that are called atolls. You go from coral to fringing reef to barrier reefs, ultimately to an atoll. And there's a video that talks a little bit about these as well that I'd like you to take a look at.